In this video, we'll dive into all the essential sorting algorithms you need to know, from bubble sort to bucket sort and all in between. We'll explore how they work, their efficiencies, and when to use each of them. Let's start with bubble sort, which is often the first stepping stone for beginners. On each pass through the array, we compare neighboring elements and swap them if they are out of order, ensuring the highest or lowest value bubbles up to its final position per iteration. Although the bubble sort is simple, its time complexity is O of n squared, which translates to noticeable sluggishness as list size grows. However, it uses minimal O of 1 space complexity, making it somewhat practical for smaller inputs. So it is simple yet not the most efficient for large datasets. Moving on to selection sort, which operates like sorting a hand by repeatedly picking out the lowest cards. So we divide the collection into two parts, a sorted portion and an unsorted portion, and we repeatedly find the minimum or the maximum element from the unsorted portion and swap it with the first element of the unsorted portion. Selection sort shares bubble sort's time complexity O of n squared, making it similarly inefficient for large datasets. However, its space complexity is O of 1 and is practically efficient with small or partially sorted datasets. Next, we have the insertion sort, which works by gradually building a sorted portion of the collection. It iterates through the unsorted part of the collection, comparing each element with the elements in the sorted portion and inserting it at the correct position. But since it has two nested loops, its time complexity is O of n squared in the worst case, but it can be O of n if the array is mostly sorted. And space complexity is constant O of 1 because we are not using any additional space. Next one is the merge sort, which is a divide and conquer algorithm. It recursively divides the collection into smaller halves, sorts them individually, and then merges them to obtain the final sorted collection. And this merge operation is basically a merge helper function which combines two sorted subarrays into a single sorted array. Merge sort's time complexity is O n log n, unshaken by the initial order of elements. And this reliability comes at the cost of additional memory usage with a space complexity of O of n, because we are keeping the sorted arrays in our memory. It's optimal for larger datasets due to its consistent performance. Quicksort is another divide and conquer algorithm that selects a pivot element and partitions the collection into two subarrays according to whether they are less than or greater than the pivot. It then recursively sorts these subarrays. Its average case time complexity is O of n log n, its space complexity is O of log n due to the recursive stack calls. However, its worst-case time complexity can be O of n squared, particularly with poor pivot choices. Next one is Radix Sort, which takes a unique approach, sorting numbers by their individual digits. It operates in linear time with time complexity of O n times k and a space complexity of n plus k, where k is the number of digits and n is the size of the input. This type of sort works well with integers and strings, but it is not suitable for sorting floating point numbers or data types that don't have a clear digit-based representation. And finally, we have the bucket sort, which is like sorting fruits into different buckets based on their type. It divides the array into different buckets and then sorts them individually and then merges them. Bucket sort can perform exceptionally well with an average time complexity of O n plus k, but requires additional space with O n times k to store its bucket. In summary, bubble sort, insertion sort, and selection sort are simpler algorithms with higher time complexities, and they are often taught for educational purposes to help students understand the basic principles of sorting and algorithms. But in practice, these algorithms are rarely used for large datasets due to their inefficiency compared to more advanced sorting algorithms. Merge and quicksort are more commonly used in real-world applications due to their better performance on larger datasets. Merge sort provides stable O of n log n performance and can be more efficient for larger datasets or datasets that are already partially sorted. Quicksort also provides O n log n performance on average, although its performance can degrade to O n squared if the pivot value is not well chosen. However, with good pivot selection strategies, quicksort is often faster than merge sort in practice and widely used in many standard library sorting functions. Radix sort and bucket sort are special purpose sorting algorithms that can be very efficient for certain types of data. Radix sort, for example, is efficient for sorting integers or strings and provides O(n) times k complexity, where n is the number of elements and k is the number of digits and characters. However, it requires additional space and is not efficient for data types that don't have a digit or character representation. And bucket sort is effective when the input is uniformly distributed across the range and can provide O of n plus k complexity, where n is the number of elements and k is the number of buckets. Comparison-based algorithms sort elements by comparing them against each other to determine their relative order. On the other hand, non-comparative algorithms do not sort by comparing elements. Instead, they sort based on the numerical or bit-level properties of the elements.